Okay, good morning, everybody. Welcome to Prague. Welcome to CHES conference. Let me introduce Hana Kubátová, General Co-Chair of CHES.
And let me introduce Martin Novotný, who is the most important person concerning this year CHES.
So you finally made it to Prague. Prague is the capital of Czech Republic. We are in the Central Europe. It is a very historical city. Dominant of Prague is the Prague Castle, and the Prague Castle also became the logo of the CHES conference. We have the oldest university in Central Europe, Charles University, which was founded in 1347. And this picture is a very typical picture of Prague because it depicts Prague Castle with the cathedral and the Charles Bridge, which is below. The Charles Bridge was founded, or the foundation stone was laid down in 1357. So this year we celebrated 666 years from its foundation. By the way, okay, there was maybe you may think that we are finally to the east in Europe, so the CHES made it to the east. But the fact is that there was one CHES that was even further to the east in Europe. It was in it was in Vienna in 2007. It was my first CHES, so Vienna is even further to the east. Okay, so this building, Prague Congress Center, was built in 1981, and it was opened by 16th Assembly of Communist Party of Czechoslovakia. And after that, there were some other events, like, for example, the Assembly of International Monetary Fund and the World Bank in 2000. And in 2002, there was a summit of NATO. And in 2006, Pluto was excluded from the list of planets in this building. It happened here, yeah. It happened in the Congress Hall, which is just behind your back. So, yeah, we are very close to the original site of Prague, because Vyšehrad, the subway station, has the name Vyšehrad, and Vyšehrad is the seat that you can see from the terrace. So if you go to the terrace and look to the left, you would see probably the church, and the church is inside the fortress, and the fortress was founded in the 10th century or so, and it was the seat of the royalty, of the ruling family of the Czech lands in that time. And after that, it moved to the Prague Castle. Prague Castle was the seat of the king, and nowadays it is the seat of the president. And there are many legends connected to Vyšehrad. So, for example, about the Princess Libuše and her husband Přemysl, and about Horemír, who was rescued by his horse Šemík, who jumped out of the Vyšehrad to the river Vltava. So if you go there, I can recommend it to you to go there, because there is very nice park and relaxing zone. So, and you can see all the Prague from the walls of the fortress. And you will also see the view to the Vltava River with all the bridges and so on. And so you will see it is about, I don't know, 70 meters high. So the Šemík jumped out the 70 meters to the Vltava River and rescued Horemír. So this is about Vyšehrad. So you can go there. It is just 5 minutes from here. It is not planned to go there during the sightseeing tour. So go there now during the lunch break or so. It's very nice chill out zone, and many pubs are there. So now organizational things. We kind of ask all the speakers to upload their slides on time, and which means at the latest 24 hours prior to presentations. Just keep in mind that your presentations are scheduled for 20 minutes talk and 5 minutes for questions and answers, and be here or in the other room 5 minutes before the session starts. And please, online speakers, upload all your videos, so we need them. For the audience that is online, please mute your microphones, and you can ask questions only via chat. So, and there will be a rump session today. So we have the long day today. We end up at 10 p.m. So if you want to tell us something funny, I hope for something funny, the session chairs are Francesco Regazzoni and Guido Bertoni. And they asked me to tell you to send your proposals for the rump session to the email address chess2023rump@gmail.com. and do that until 3 p.m. today, please. Yeah. So to be included into the ROM session. So now Hana will tell you something about the program.
Okay, the program, all actual informations, it's possible to see on web page of this conference, CHES conference. Here is the program. Yeah, here is the web pages, and you can look for everything and every information about the conference. Maybe to improve the location, because the Congress Hall is relatively large building, and we use only 2 spaces here for presentations. From yesterday, who remember what was yesterday? It was Sunday tutorials. Here was 2 sessions, and now only 1 session here is. And other session is in 2nd floor, and where the common presentation will be given for all participants of conference. This presentation will be streamed to 2nd floor, to the South Hall 2 in the 2nd floor. And all things important will be such coffee breaks, lunch, and light dinners will be preferably in Forum Hall foyer in 2nd floor, and some smaller refreshment during the coffee breaks will be in 3rd floor, because we have more than 500 participants to be served fast, and to make service proper for all participants. And therefore, I would like to emphasize that the best services is possible to look at foyer 2 in 2nd floor. And to see it more graphically, main CHES services are in 2nd floor. Here is the hall in 2nd floor for parallel session 2. Downstairs, this is 2nd floor. And this is also visible on web. And here, everything is visible on web, only in these graphical things. And this is the 3rd floor, where we are now. We are here. And here is main South Hall 3 in this place, in this 3rd floor. And here is also a poster session and small gathering that in 2nd floor. If anything will be unclear, do not hesitate, ask anybody in this yellow t-shirt. And here is some information. I would like to give you some information about social events. The main social event will be in Wednesday. It will be guided walking tour of Prague. Everything will be given to participants in English. It will start this in front of this building of the venue of the conference at 30 minutes past 4 p.m. And end of this walk will be at the place where banquet place will be given to you. It is in front of Joffin Palace, and this banquet will start 30 minutes past 7 p.m. Organization will be the following. You will be divided into groups approximately containing 30 participants. We will not use any buses because we are in the center of Prague, and this problem with cars and buses due to traffic, and therefore we will walk. Or you can use public transport. Every participant obtains such tickets to use this public transport because this is faster, easy, and I can recommend it to you. And these groups are scheduled to leave continuously between 30 minutes past 4 p.m. to 5 p.m. and the latest groups will leave at 5 p.m. on Wednesday. Take care about that. Don't to miss this time. Okay. And the banquet will be at the Šofín Palace. At this address is Slovanský Ostrov, and this is the number. This is not important. It's not necessary. It is visible. It is on the bank of Vltava River, and all informations are also in our webpage, which is accessible for all of you. And there will be some conference dinner, and you can listen some music. The music will be given by music group Olnies. This is the name of this group. And the interesting is that the member of this group is Professor Jara, who is specialist from our former faculty of electrical engineering, and our former colleague, and but he is specialized of computer graphics, who is interesting in computer graphics. You can ask him about such things concerning our embedded and security issues. And some informations about glasses, special gifts for you. I must say this is not used for, it is not intended to use it for drinking beer here, which are offered, but it's possible. This is such.
Bar is open already. So.
No, I'm afraid that not yet.
It is.
Yeah?
Yeah, it is.
Oh, fantastic. Some problems with that.
Okay, just
sorry.
One thing about the beer glasses, if we still have plenty of the small ones, 0.3. So if you have the 0.5, and if you find out that it is too big for your luggage, just do not hesitate to come to the registration desk, and we will replace it for you. So no problem. So.
Yes, information. Two types of beers are offered to you: Pilsner Urquell and Kozel. These are typical beers, types of beer produced in Czech Republic. And I must say that Pilsner Urquell is not so alcoholic like Kozel beer, less alcoholic than Kozel beer. Only 4.5 degrees of alcohol, concerning with Kozel, which is 5 degrees of alcohol. But the difference is not so important and not so large. I prefer Pilsner Urquell. Martin too, but you can choose. And these glasses are to remember this year CHES conference, which is organized in Prague. You can see the typical Prague castle here on these glasses. And 25th, we will celebrate such 25th CHES in this year, 2023. And please do not hesitate, take this glass and drink a beer, because it is secure. Okay. This is your way.
Okay, just again, if you find some problems, do not hesitate to contact anybody in the yellow t-shirt. So we have blue t-shirts and we have yellow t-shirts, and the Wi-Fi is CHES 2023, and the password is just 1999 because it was the first CHES in USA. So just 1999. Okay, and we really appreciate the sponsorship of all the sponsors. We have 29 sponsors, so please visit their stands that are on the second floor. So we thank them. There are some logos here. So 17 sponsors have the stands there. And we can pronounce CHES 2023 to be open now. So welcome to CHES again. Okay, thank you.
Hello, good morning, everyone. So to kick off the main conference in high gear, our first invited speaker is Peter Schwabe, who is research group leader at Max Planck Institute for Security and Privacy and professor at Harvard University. He graduated from Aranha University in 2006 and received a PhD from Eindhoven Institute of Technology in 2011. He then worked as a postdoctoral researcher at Academia Sinica, that National Taiwan University. His research area is mainly cryptographic engineering, in particular the security and performance of cryptographic software. He published more than 60 articles in journals and at international conferences, presenting fast software for many primitives such as AES, hash functions, ECC, and pairings. In recent years, he has focused on post-quantum cryptography, co-authoring the New Hope and N2HRSS lattice-based schemes for the famous Google project regarding, or famous Google experiment for post-quantum TLS. He is the co-submitter of 7 proposals to the NIST post-quantum project, of which 3 were selected for standardization. In 2021, he co-established the Formosa Crypto Project, an effort by multiple research groups to build formally verified cryptographic software. I'm Diego, one of the program co-chairs, and let's welcome Peter Schwabe.
All right. Well, thank you very much for the nice introduction, and even more, thank you very much to the PC chairs and the PC committee for inviting me here, and to Martin and Hana for organizing. This is really amazing, and probably many people don't know this, but in 2019, I was asked to be program chair for CHES 2021, and when I was asked, I was told that CHES is going to be in Prague. So they didn't only organize this or did do the whole thing for this year. They actually did for 2021, for 2022, and for 2023. And twice they were told that it can't happen because of COVID. So this is an amazing effort, and I'm particularly happy now to be here in Prague and give this opening talk. So when I was invited, I was asked to speak about high assurance crypto in practice, challenges and latest results. And well, obviously, when you get asked to give this talk, then this is the title of your talk, right? So I said, well, this is the title. But then when I started preparing the talk, I realized that actually a better title would be to make crypto software boring again. And boring, of course, I mean in the sense like boring SSL, to say, well, you can just use it and, nothing interesting is going to happen. Like there's not going to be a lot of attack papers and all of this. It just works. That's what we actually want from crypto software. And let me explain this title a bit more. So what I will do in this talk is I will focus on primitives. So I will really talk about chems, signatures, maybe symmetric encryption, hash functions, and not the higher level things like not talking about TLS or signal protocol or anything. Also, I will talk about the secure channel primitives. So this is the ones that we, as I said, like chems, key agreements, stuff like that we need to build a secure channel, and not more advanced primitives like zero knowledge proofs or stuff like that. I will constrain myself here to software visible side channel attacks. And I know there's many people here who work on hardware side channel attacks where you put probes and all of this, but this is already going to be tough enough for a 1-hour talk to figure out how we can be boring again. But to make it at least somewhat interesting, I do care about big CPUs. So not just embedded microcontrollers, but I do care about, like, say, the big ARM Cortex-A CPUs you find in smartphones, or the Intel CPUs and AMD CPUs you find in laptops and servers. And when I say boring again, so somewhat around the time when I finished my PhD, that was 2011, I had the feeling that crypto software was somewhat boring. You could just tell people on the primitive side, well, use X25519 and add 25519. Use SHA-2, CHA-20, Poly 1305, or if you prefer, just use NIST P256, ECDH, ECDSA, ASHMAC. Just, there's this set of primitives that we can use to build a secure channel, and they're pretty all right. And then when you're implementing them, you follow what was called, and unfortunately still is called, the constant time paradigm, where you just say, well, you don't branch on any secrets, you don't access memory at a secret location, and you avoid certain instructions that take time depending on the input. So the div instruction on Intel, for example, would be one of those. And it felt like, okay, well, if you do this, and we kind of knew how to do this, then you'd be fine. That was my personal feeling. I was already wrong at that time, but maybe this was something that many people in the community felt like would be all right. And then a couple of things happened. I should also say, to do this is fairly little code. You can actually implement all of this without having the feature of function calls. You can inline everything, and it will work, and it will compile, and it will still be reasonably small, right? Now, multiple things happened. The first thing that happened, and this is what I've been working on for the last, I don't know, almost a decade actually, is post-quantum crypto. And if we're looking at what we are now getting with the new NIST standards is we get more assumptions. We do not just base all of our asymmetric crypto anymore on the elliptic curve discrete logarithm problem and elliptic curve scalar multiplication, but we have LWE assumptions, we have CHES assumptions, we have assumptions coming from in hash-based signatures, which is all kind of, well, non-standard hash assumptions, except, well, if you just assume that they're a random oracle. In code-based crypto, you have syndrome decoding. So many more assumptions, you have more schemes. You can't just build everything from this core elliptic curve scalar multiplication anymore. More parameters and just simply way more code. So now I've actually tried to implement Kyber, which I would think is one of the simpler post-quantum schemes, without function calls. I'll come back to why I did this. And I can tell you it's not fun. It actually takes an hour to compile alone, right? So this was not good. There's more complexity in the implementations. There's also complexity in the protocols and the proofs. But initially what I thought is, okay, well, we had these bugs that you would expect in software at the beginning, which will be caught once you have reliable test vectors. So once we have one implementation that everybody agrees is right, and we can use it to generate a lot of test vectors, you can just check other implementations against them. And I felt because we don't really use big integer arithmetic, except in isogeny-based crypto, it felt like probably we don't have these very rare carry bugs anymore, that you may have an elliptic curve cryptography where just, well, you work with these very big integers, and just if it happens to be at the very border of the sizes, then you may run into a bug. So they're very hard to find with random testing. And in lattice-based crypto, I mean, we work with polynomials where the coefficients are actually quite small integers. So I had this intuition that maybe, these kind of bugs, these really nasty ones that we don't catch with test vectors, maybe we get rid of them. And unfortunately, that's wrong. And so at least for me, this idea was completely shattered by a CHES paper last year, which presented formally verified implementations of the number theoretic transform that is used in lattice-based crypto. But also what they showed is exactly these kind of bugs. So they said, well, there's some implementation and it just works, except we can show that it doesn't work on some very, very rare inputs. So we still have these classes of bugs, but we don't yet understand them that well. And maybe, there's more classes of these bugs that we don't find with testing. Then there was another thing that happened over the last couple of years, and this is that this idea that the constant time paradigm would be enough to prevent or to protect against software visible side channels would be enough. So there was, I think, the Spectre and Meltdown papers, and in particular the Spectre paper, completely shattered that worldview. So it really showed that this isn't enough, and then various other new microarchitectural attacks came out that put into question this worldview more and more. And the nice thing is that until very recently, all of these attacks came with nice logos. So you can compile a very nice, colorful slide like this. And you may notice that some recent attacks are missing on this one. Like, for example, the downfall attack by Mogimi that was presented at Usenix last month. And the reason is that apparently this trend of coming up with logos for attacks has stopped. I did not find any Downfall attack logo. Luckily, there is an Italian thrash metal band called Downfall. And of course, you can rely on thrash metal bands to have logos. Anyway, so I encourage all of the people working on attacks, please keep doing logos. I really love this. But so what we have now is we have much more complex crypto that we need to implement, post-quantum crypto. And we have a much more powerful attacker, even in a software-constrained environment. So we, for example, have to actually think about how to protect against Spectre. Potentially a few more, like there's this Hertz bleed up on the top right, which I don't really know yet what we can do, how we protect against it. There's a few other ones where CPU producers said, okay, this is a bug, we're going to fix it in hardware or we fix it in microcode, and then maybe we don't need to worry about it in software. Now, the big problem that I think we're facing is that we're trying to tackle this complexity with tools that are from the last century. Can I just have a show of hands here? Who has implemented crypto software in this room? Okay. Who used C? That's pretty much the same number of hands, right? So I think it's still, I'm not criticizing anyone. I mean, in the NIST post-quantum competition, it was mandatory to submit code that was in ANSI C. They didn't actually say what they mean with ANSI C. And while the API was such that you can't actually use ANSI C, but it's still a very, very common thing. And then, well, what is wrong with C? Well, there's the obvious things that I think everyone here in the room can say. We have no memory safety. We have very finicky semantics. So we have, of course, undefined behavior. We have implementation-specific behavior. And we looked at a lot of implementations submitted to NIST PQC, and I think none of them was actually properly portable. So if you throw it at a big endian machine, it would fail. If you throw it at a machine where integers don't have 32 bits anymore, they would fail. All kind of different failure modes there. We have some context-specific behavior. That's in particular when you combine with assembly. For example, things would only work if your input pointers are aligned. And well, if you don't align them, then they crash or they do something else. And we have no optional runtime checks. So what I mean by this is that when developing software, it's sometimes really nice if the language or the environment tells you when your integers are overflowing, except when you explicitly say, I want them to be overflowing, right? When you look at this, if I was giving this talk at Real World Crypto, they would already be saying somebody, but Rust, right? Let's just move to Rust. In Rust, we have all of this. We have memory safety. The semantics are more clear. I mean, the semantics are basically, there's one compiler, and whatever that compiler does is the semantics. You do have mandatory initialization of variables. You do have these runtime checks. So it's actually super nice when you're programming in Rust and you make this mistake that I see about half of my students making in the crypto engineering course. When you're multiplying two 32-bit integers and you're assigning it to a 64-bit integer, they're assuming that, well, you compute the 64-bit result and you're putting it in there. But of course, what C will do is it will just throw away the upper half and then do the assignment. And half of the students make this mistake. And in C, it's actually nasty to find. In Rust, the language will tell you, you have an overflow here. You need to deal with it immediately. This is really great. Of course, when you're deploying the software, you can remove these checks. There's another problem, though, and this is not just a problem with C, it's also a problem with Rust. And this is that they have a lack, the tools have a lack of security features. And there's a paper from 2018 by Simon Chisnall and Anderson, which is called What You Get is What You See. I highly recommend you take a look at the paper. It's great. Actually, the whole abstract is already a money quote that I could have copy-pasted on the slide, but I decided to put only the first sentence, which is that security engineers have been fighting with C compilers for years. And probably everyone who had the hand up earlier would say, yeah, I kind of did, right? And I would say that the underlying problem of this is that these compilers have no concept of what secret and public data is. The languages don't have that concept and the compilers don't. So the compiler doesn't even know what data needs to be protected. And as a consequence of this, there's no preservation of constant time. So even if you're avoiding secret memory access and secret branches on source level, the compiler will just happily reintroduce them in some optimization stages later. There's multiple examples of this, and with every new generation of compilers, the compilers get smarter and smarter. So even some code that may be okay today may not be any more tomorrow. We actually had a fun discussion recently when I updated the Kyber software to incorporate some changes that NIST decided to apply to the standards, and I sent it to my co-authors, and John Shank replied and said, yeah, you know, this looks a bit fishy to me here. smart compiler could be optimizing this and actually introduce a branch. I said, no, the compiler can't, because this is in a separate file. And in a separate file, the compiler needs to translate that separately, so the compiler doesn't have the knowledge to do that optimization. And then John replied and said, but what if a user copies that file like and inlines everything? I said, well, yeah, users shouldn't be doing this. I mean, this is a security feature, right? And he replied, well, we actually did. So, so it's super finicky, right? Like the code, as I put it out, I think is fine, but this is almost by coincidence. We have very, very limited help in protecting against microarchitectural attacks, well, against the more advanced ones than classical timing attacks. We have no erasure of secret or sensitive data, no support for that. So when we're seeing this, the immediate reaction would be basically what this 2018 paper did to say, okay, let's fix these tools. So we argue that we must stop fighting the compiler and instead make it our ally. Sounds like a very great idea. And actually that paper went ahead and did this, at least for some examples. Most notably, what they did is they implemented secure erasure of data in LLVM. It's really cool. It's online, so you can go to the GitHub repository. The problem is it never got adopted in mainline LLVM. And, well, maybe the patches still work at the moment. In 5 years, I'm relatively sure the patches won't work anymore. And this is an experience that I've made also in other contexts, that you can try to fix the tools like LLVM or GCC and get security features in there, but they're not actually going to be adopted in the compiler. Another example is we had in 2020 at the High Assurance Crypto Software Workshop, HACS, we had a working session on getting secret types into Rust, C++, and LLVM. So first of all, on the source level, be able to express which data is secret and public, and then have the compiler, pull this information through the whole compilation stages and disable certain optimizations on secret data that would introduce leakages. That was the idea. It was a great idea, and there's even a draft RFC online for Rust. I think there's also a draft RFC for LLVM, but I think that one is not public. And well, at the time I was super optimistic, and I asked a PhD student of mine to look into this and maybe implement this. Amber, luckily, before Amber spent too much time on this, I talked to Chandler Carruth, who's working on LLVM at Google, and he told me for my whole team, this would be a multi-year effort. And then I said, okay, maybe not the best topic for a PhD student. He took this home and he actually said he's going to work on this with his team, but Chandler's team is busy doing other things. Chandler is very busy doing other things. So I checked with him late last year and there was no progress yet. So even though there are people at LLVM who agree that this is important, this is really a massive effort. And actually the effort is so massive because there's, 8 intermediate languages or something on that scale. And you need to change every single compilation stage, and you need to change every single one of these intermediate languages to introduce that type system. And you touch basically all of the compiler at the same time. Another example is specter protections. So in 2019, Chandler Carruth, he came up with a countermeasure in LLVM, which is great. This is actually the one positive example that I have for a security feature that did make it into compiler. I will talk about this a bit more later in the talk. But this countermeasure in the description already is completely admitted. It's not sound. It does a lot of good things, but it does not defend against secret data already loaded from memory and residing in registers. That's what the description says. So in 2023, in a recent paper that we had at Usenix, we said, well, let's revisit that. Let's implement it and give a really principled approach where we can really guarantee that Spectre v1 attacks are really prevented by this. And we implemented it, we benchmarked it, we reported it to LLVM, we sent patches to LLVM. There was a bit of a discussion, and the outcome of the discussion at the end was won't fix. So LLVM decided not to accept the patches. And the reasoning was, well, first of all, nobody's using the SLH flag anyway, so nobody's protecting against Spectre v1. And it would be additional code in the compiler that they need to maintain. And there is cost in code maintenance. I'm not saying this is a bad decision. It's a trade-off decision. And it makes sense probably for LLVM, but we just won't get these features realistically in mainstream compilers. I think we should still try to push for it because I think it's important. So what's the alternative? Well, the alternative is to actually change the way how we're building crypto, change languages, change tools, and to to this end, the approach that I want to advertise a bit in this talk and give you an update on is high assurance crypto, which the idea is that we work more strongly together with the community in programming languages and formal verification, and we give really strong computer verified guarantees on correctness and security, also cryptographic security of cryptographic implementations. So in 2021, late 2021, we started this Formosa crypto initiative. And first, when you're wondering where this nice logo comes from, this is the Formosan black bear, and it's endemic to Taiwan. And well, beautiful logo. It actually naturally has this check mark on its chest, right? So you see this check mark. It's great for formally verified crypto. And by the way, Formosa also stands for something like formally verified open source amazing crypto, I think. Something along those lines. And this builds on a lot of existing previous work, this Formosa crypto project. We're using the EasyCrypt proof assistant for formal reasoning about implementations and about cryptographic constructions. We use the Jasmine programming language that I will talk about quite a bit more in this talk. And we have a cryptographic library, which is focusing on post-quantum cryptography with strong formal proofs. And sort of the big goal that brought these existing projects together and the people together and the whole project together is, well, we will see this migration to post-quantum cryptography the next couple of years. Let's try to get really high quality software ready that people can drop in and use with these strong formal guarantees. We have a core community of, well, 30 to 40 people. So we're meeting 3 times a year for a week on a retreat and work together. We also meet regularly virtually. And we have a discussion forum with more than 180 people. So this is an open Zulip server. And I'll have the links at the end of the talk. So if you feel interested, then of course you're most welcome to join and learn about this. So this is a huge effort, right? So this is like what I'm talking about is joint work with many people. This is probably not even a complete list, but there's 4 names that I would particularly want to mention. That's Benjamin Grégoire, Jean-Christophe Lechenay, Santiago Arranz-Olmos, and Vincent Laporte, because they are the people who really put all of the work into the Jasmine compiler. And I'm mostly just using the Jasmine compiler and telling them about all the things that I wish I had and you know, suggestions for improvements. They're really doing amazing work on this tool chain, and I think they deserve actually almost all of the credit for what I've been talking about, what I will be talking about. Now, the general tool chain in Jasmine, or sorry, in Formosa crypto looks roughly like this. And now I need to see if this pointer works. Yeah, it works. So for me as a crypto engineer, it starts with a Jasmine program. So we implement something in Jasmine, and I will show you what this looks like. Now this program enters the Jasmine compiler. And out of the Jasmine compiler come 2 things. So one thing is it compiles to assembly. So that's the code that in the end we just assemble and run. And that is a certified compilation, which means that we have formal computer verified proofs that the compilation is correct. There's also all kind of automated checks that the compiler does on the code, and I will talk about this a bit more. We can also extract from the Jasmine program an EasyCrypt model of the Jasmine program. So it's basically, well, in EasyCrypt syntax what the Jasmine program does. And then on the other end, we have an EasyCrypt specification. And the specification is essentially, you take some standard, you take an RFC or a NIST standard, and you go through the pseudocode there, and you rewrite the pseudocode in EasyCrypt syntax. So now we have a very high-level description, this EasyCrypt specification, and we have the model that comes out of the program. And then we can do an interactive proof that the implementation is a correct implementation of the specification. And also, of course, on the specification, we can run all kind of interactive security proofs. And what I will do in the rest of the talk is I will first give just on one slide a bit of overview of stuff that has been happening on this side. Now, this is not work that I was very much involved in. I'm not a co-author of any of these papers, but just for you to give some references for those who are interested, some papers that you might want to take a look at. Then I will talk most of the time about this right side. So what you're getting if you're programming your crypto in Jasmine, and why you might want to do this even if you don't care about EasyCrypt and all of that formal reasoning at all. And then at the end, I will give a very brief look at this like tiny little arrow there, the interactive proof that actually establishes the functional correctness of our implementations. So with regards to the results on EasyCrypt and formal proofs in EasyCrypt, there's 4 papers that I think stand out in particular in this effort of getting a high assurance post-quantum cryptography ready for deployment. There was one paper at CCS 2021 that extended EasyCrypt to support also large classes of proofs in the QROM. So basically, traditionally, EasyCrypt was not able to consider quantum adversaries. And of course, if we care about post-quantum cryptography, we kind of need to consider quantum adversaries. So this paper extends that functionality and introduces EasyPQC. Then there's a paper that was at Crypto 2022 that proved, gave a computer verified proof for the int CPA security of the encryption scheme that is underlying Saber. And that's a paper that I like a lot because Matthias Myers, he worked on this in his master's thesis. I was just second reader of the master's thesis. But before he did this, he had a research internship also with Andreas Holzing and me. And in that internship, he implemented the Saber encryption scheme in Jasmine. And that was one of the first times that I felt like, okay, I'm just throwing some Jasmine implementation project at a student and just see how it goes. And it went really well. Also Matthias is really good. You might not want to do this with every student, but it worked really smoothly. I mean, he had a few questions, of course, right? But you can just use it. At Crypto 2023, there's a paper that formalizes the security proof of dilithium. And actually, it says it's fixing the proof. So that started when Yi Li was visiting us, and his idea was to look into mechanizing the proof, and then at some point realized that the proof actually isn't correct. And then that turned into a much bigger project involving more and more people that fixed the proof and then also mechanized it to make sure that this time it's correct. And then finally, also this year at Crypto, there was a paper on machine-checked security for XMSS. So that's hash-based signature scheme, stateful. That is already standardized. And that had a security proof. And again, somebody pointed out that the security proof is actually not correct. And in this paper, they're basically introducing a somewhat stronger assumption, and then with it, somewhat stronger assumption, proving everything, and making sure again that the proof now is actually correct because it's verified in EasyCrypt. Okay, let's come to implementing crypto, the stuff that many of us do here at CHES. I think we can agree that at a very high level, we want 3 properties from cryptographic software. I want efficiency, we want security, and we want correctness. And they're not completely unrelated, like something that is not correct is probably also not secure. But it still makes sense to separate them. And for efficiency, I mean, very often we're looking at just speed. And actually for this setting that I have here where I say, okay, we're looking at big CPUs, we're looking at only software side channel attackers, probably we care mostly about speed. We may also care about RAM usage, binary size, potentially energy consumption. In terms of security, we don't want to leak secrets. That's sort of the core security property. So we want code to be constant time in this traditional sort of broken sense. I think want to resist Spectre attacks. I think we should actually get there. And then come the hardware side channel attacks that we also care about, but not in this talk. And then we have correctness. And correctness, of course, means functional correctness, but we also care about memory safety, because if a program isn't memory safe, then it's certainly not functionally correct, thread safety, and potentially termination of a program. So how does Jasmine and programming in Jasmine help you with this? Well, Jasmine is a programming language that was introduced in 2017. And in this paper, by the way, all the links to the papers, or the titles of the papers are links that you can click and you'll be taken to the PDF. I'll have the slides online later today, so I didn't put the bibliography at the end. I just made everything clickable. The language looks very much like C. I'll have a few examples on the next slides. But it feels, when programming, it's a bit treacherous because you feel like you can program like in C, but you cannot. It's more, you should do assembly in your head. And what that means is that generally one line in Jasmine translates to one line in assembly. We have very few exceptions, but they're very highly predictable, so that one line translates into 2 or 3 assembly instructions. The compiler does not schedule your code. The compiler does not spill registers, which also means that if you're using more live variables than you have registers available, the code won't compile. So it's really, in that sense, very close to assembly. The compiler, as I said, is formally proven to preserve the semantics of the program, and it's also formally proven to preserve the constant time property. So if your source doesn't branch on secrets or accesses memory at secret locations, then neither will the compiled assembly. I should also say it's probably, as an introduction to Jasmine, not the best thing to look at the 2017 paper. This has improved a lot. It got function calls. So that was my first attempt to implement Kyber in Jasmine when it took an hour to compile, and I said, this is not going to work. So at the time, it didn't have function calls. So what does a hello world look like? You would think we're just starting, well, take a C code like that and do it in Jasmine, but that's not going to work. So in Jasmine, we don't have a main function, usually, not yet. It's basically meant to implement the leaves of your function tree, of your call graph. And we also, at the moment, still don't have I/O in Jasmine. So really what you're doing is at the end of your call graph, you say, we want to have this cryptographic primitives implemented. I don't know, we want to have this Diffie-Hellman, or we want to have this key encapsulation implemented, and you put the arguments and you get the output back, that's it. So here would be sort of a very simple hello world, which gets a 64-bit integer and adds 42 to it. It's a rather boring thing, but you can see it looks, well, almost like C, right? I mean, so the output is a bit different. Important thing is this export function. So only the export functions are actually visible from the outset for the caller. It's going to respect the C function call ABI. So you can just call this function from C, and then, well, it will do the boring thing of adding 42. For somewhat more interesting examples, I have this starting tutorial, getting started guide, which tells you how to install the compiler, how to also install EasyCrypt, and then goes through one example. And usually at this point, I would be showing a small demo, but then I don't have my own laptop here. And there's also, I think this is Zoom stream, so I knew already that this wouldn't be working. And so I just put the example code here. What this example code does is it's just taking two arrays of 32-bit integers of a fixed length, which is 128, and just adds them component-wise. And it does this in 3 different ways, just to illustrate different trade-offs when programming in Jasmine. So the easy way, first way to do this is in a, oh, sorry, no, it's, what did I do? Can somebody do Control L? Don't know what I did here. Okay. So we do this for loop, and a for loop gets as an index through the loop an inline int, which will be expanded at compile time, and the whole loop will be unrolled. So every for loop is always fully unrolled. We could say we don't want the loop to be unrolled, in particular for very long loops, even if we know the length, we might not want this, and then we can use a while loop. And a while loop, we need to say the index is in a register, we need to actually do the increment as an instruction, because it can't be done at compile time. But still, I mean, it looks very much like a C program. So you need to explicitly say make the loads explicit and all of this, but then it's not so crazy. We can also say, well, we might want to use vector instructions. So this is for an Intel CPU, and we might want to use this VP add instruction to always process 8 32-bit integers at the same time. And there's this sort of intrinsic support for all of those things. Okay, so how are we doing in terms of efficiency of this? Well, basically, we can do everything in Jasmine that you can also do in assembly, almost everything, which also means you have almost full control over what's happening. You have architecture-specific implementations, and I'll come back to architecture support later. It is easier to write and maintain, though, than assembly, I would argue. So we have loops, we have conditionals, we have function calls. We can also have functions that get inlined. We can just say this is an inline function and it will be inlined, but it behaves like a function. For example, we have function local variables, also in inline functions, which in assembly you don't have. We have register and stack arrays. Register arrays are actually a pretty cool thing. So if you just have, like, I don't know, 8 values that you want to treat as an array, you can just say it's a register array. You can iterate over it in a for loop and it will be automatically expanded. We have register allocation, we have stack allocation. As I said, no spill code generation though. So you can have way more variables than registers, but you can't have more live variables at any particular point. Then there's some limitations. So when I say you can do almost everything, there's no raw pointers and you can't do pointer arithmetic. So you can't get the address of anything that's living on the stack into a register and then manipulate it. You also have, at the moment at least, very limited control over register allocation. So you say this is a 64-bit integer register, but you can't say at the moment which one you want it to be. But those two constraints, at least for what we're aiming for here, to make it efficient and protected against software visible side channel attackers, is probably just fine. So in other words, my experience is when writing cryptocode in Jasmine that it's as efficient as hand optimized assembly. There's really no reason why you would be slower, except that you don't put the same effort in or something like that. In principle, you can just do the same thing. Let's talk a bit about security. So the constant time paradigm, the way that we're ensuring this is that on source level, we have a security type system. So we do say for every variable, if it's secret, if it's public, a lot of that information is inferred by the compiler. And then we're basically tracing this information flow. So when you have any operation which has a secret input, then the output has to be secret again. So then branch conditions and memory indices need to be public, otherwise the type checker will fail. And that's in principle what we can also do in Rust. So Rust has a type system that allows you to implement this, and it has been implemented in the secret integers crate. The problem is that when you do this on source level in Rust, the compiler will afterwards mess with it. Whereas in Jasmine, we have the guarantee that the compiler will not mess with it. Sometimes we need to say that something that was secret needs to become public now. And the most obvious example of this is a ciphertext. So obviously, ciphertext depends on a secret key. It depends on a message, which is both secret. But you're sending it over a channel, so this is as public as it gets. And then we need to declassify things. And declassify is an explicit statement, and it creates, in a way, a proof obligation in EasyCrypt when you're extracting. So you need to say why this declassify is okay to do. And usually, this just says, well, we apply the following assumption that we have that, for example, AES is a secure block cipher, something like that. Now, this is only part of the story, though, because I said we want to not just protect against classical timing attacks, we also want to protect against Spectre. And just a brief recap on what Spectre does, here's some Jasmine code that would be Spectre vulnerable. So we have a public array public, we have a secret array secret, and we have a loop. I need to point here. Yeah, we have a loop here which iterates over the public array and then leaks the values that it loaded. And that's totally fine in a traditional timing attack scenario because we're only leaking public values. The leak function could be anything. Typically, just use it as an index into some lookup table, for example. Speculatively, though, what Spectre will do is the CPU will go through that loop, and after it has done 10 iterations, it will most likely speculatively do an 11th iteration, which means it will start loading out of bounds from this public array, which means it will load from the secret array and then call the leak function on something secret. Now, at some point, the CPU will notice that it did something stupid and say, okay, I'll undo everything in the architectural state that I did in this extra loop iteration. But it will not undo what it did in the micro-architectural state, like in the cache. And then that can be exploited by Spectre. In fact, so Spectre v1 is often called speculative bounds check bypass, which is exactly this example, but it's a bit more subtle than this. When we're implementing cryptography, then you may have code like this, where we're doing an AES. So we're going through the round of AES. We have the round keys here. We're calling AES enc, so just Intel intrinsics to do this. And then after 9 rounds, we do the last round, and then we're returning the state. And we're declassifying here because, of course, after we've done the 10 rounds of AES, this is ciphertext. This is something that is totally fine to leak. Now, what happens if an attacker obtains that state and uses it as, say, a lookup index into something? Well, what may happen is that the loop gets speculated to abort early, and speculatively, this leaking of the state happens after just 1 round of AES. And we know that this is not exactly secure, so we need to make sure that we're not speculatively declassifying early. And that is something that we had in a paper this year at Oakland Security. And we showed that this is actually potentially a problem depending on what you're doing with state that gets declassified and released. So what can we do against Spectre? Well, first thing we can do is we just disable all speculation at branches. It's very expensive, but we can do it. We can put an elfence instruction to prevent that. The somewhat better approach is the speculative load hardening that I mentioned at the beginning of my talk that Chandler Carruth came up with in 2019. And the idea is that you have one register which contains a misspeculation flag. And whenever we're doing a branch, we additionally use arithmetic to update this misspeculation flag. So do, for example, a CMOF instruction which isn't speculated. And now whenever we're executing and we're loading something from memory, we're either masking the address or we're masking the loaded value with this misspeculation flag. So in a regular execution, this will just give us the correct value. And in a misspeculation execution, when this misspeculation flag is 0, it will just give us 0. So that means that during misspeculation, we're leaking a constant value, and that's not a problem. That's the idea. It's an LLVM since version 8. The performance overhead is still pretty large. Also, as I mentioned, there's no formal guarantees of security, but it works against this bounce check bypass in practice pretty well. But then we came up with a question like, do we actually need to mask and protect all of the loads? And it turns out that we don't. Because if we're loading a value, and then that register value is never entering any instruction that leaks the value, then we don't need to mask it. I mean, it's just not leaking anyway. So that's fine. And we know that everything that is secret won't enter a leaking instruction. So everything that we've already typed as being secret, when we're loading into such a secret register variable, we don't need to mask it. We only need to mask the loads into public registers. So based on this idea, we extended this type system and we said, okay, let's have 3 levels. So we have public, which is just public. We have secret, which is just secret. And then we have transient. Transient means it's public conceptually, but in a misspeculated execution, it may contain secret data. And then we maintain this misspeculation flag. So we're initializing at the beginning of the execution with an elfence instruction. So we know that we're not misspeculating at the beginning. And then every branch, we're using this set MSF, which is essentially doing a CMOF based on this condition of the branch. And whenever we do a branch without doing the set MSF, that invalidates the misspeculation flag. So we don't have a valid one anymore that we could use. And then we can trace that through the type system. And then we have 2 operations to lower the security level. We have the protect, which goes from transient to public, and that one will do the masking with the misspeculation flag. And we still have the declassify, which goes from secret to transient. And that does nothing. So we can just go to transient, and then if we actually want to leak that value afterwards, we need it to be public, so we need to go from transient to public, which needs to introduce this protect. As before, we allow branches and indexing only for public values. Okay, so in crypto, actually, we're in a somewhat special setting, because first of all, we know which inputs are secret and which ones are public. This is not the case for general software. Most of the state that we're working with is actually secret. Any crypto implementation that gets some secret data, the first thing it will do is it will mix the secret data with the public data. Let's say almost every crypto implementation. And then afterwards, all of your state is secret. So most of the loads, they don't need protects because they're anyway going into secret variables, and those don't leak. We can even mark additional inputs as secret, and that would be understood as, well, you can also put public data here. We're just promising you that we're not going to leak it, which is also fine. And that means that there's additional loads that we don't need to protect. If we have a spill, so a store and then later a load, and between those two, there's no branch, we also don't need to protect, because either if it's public or secret, whatever we stored there, we know that we're loading the same thing again. And then we can do some trick where we're not spilling to memory, which would have this out of bounds problem, but we can also spill to MMX registers, which are not really used by anything in cryptographic implementations otherwise. And that's a paper that also we presented at Oakland this year, which got a distinguished paper award. Now, you may ask, how fast is this? We know we can protect against Spectre v1. We know we can just disable all speculation with elfence, which is, I think, like a 300% overhead on common benchmarks, so it's very expensive. So we implemented this on all of libjade, on this cryptographic library that we have in Jasmine. And here's the performance impact on symmetric encryption with CHES 20. So you see that if you have very short messages, I can actually do this here as well. Very short messages, then you do get a noticeable overhead. This is not from any of the protects. This is just from the initial LFENs that we need because we're transitioning from C code to Jasmine code, and C code doesn't give us the misspeculation flag. So we need to get it once in a clear state. And this overhead goes basically away as soon as we're getting longer messages. I mean, we still have that LFENs, but then that cost gets amortized. So we get to somewhere like at 0.13%. We did this also for poly 1305. Here you see that same effect much more dramatically because poly 1305 authentication is even faster. So you see a massive overhead, well, say at least very, very significant overhead for very short messages, but also for long messages, we're solidly below 1% on overhead. For asymmetric crypto, we did this for X25519, so elliptic curve scalar multiplication. We even get a negative overhead. We benchmarked this quite carefully. It's probably something with code alignment or something like this. We didn't need to do anything really to protect it. It was already secure. So yeah, this is somewhat unexpected. But you see that also for Kyber, where we did need quite a few protects, we're still like solidly below 1% for Kyber as it's being used right now in TLS. So in other words, when we have such a type system and when we have the tools that support us to really protect code, then we can get extremely efficient code. This is, by the way, the performance numbers there. We didn't start with slow code, right? This is state-of-the-art, fully optimized, vectorized everything code in Jasmine. And it's about as fast as existing assembly and C implementations. And we can get this Spectre v1 protection for almost for free if we have the tools. Let me talk a little bit at the end about correctness and as part of that, as memory and thread safety. We don't have global variables in Jasmine, so we have thread safety, except of course, if you pass as a pointer to memory from the outside that is shared, and then, well, things may go wrong, but that's not really under the responsibility of Jasmine then. There's a static safety checker. So Jasmine has some constraints, as I said, very limited what you can do with pointers. And these limitations allow Jasmine to make sure that a program is safe at compile time, which in general is impossible. It uses these language limitations. It ensures termination. It ensures memory safety. And this is a separate compiler pass. So it's not in your, like, we're not doing this every time we're compiling a program. And the simple reason for this is it's very slow. So if you're doing this for Kyber, encapsulation takes about a day. It is sound, but it's not complete. So there is safe code where the safety checker will not be able to understand that it's safe. And then sometimes it helps if you're adding some annotations. So for example, for a while loop, you can say, oh, this while loop is bounded. You can just unroll it in the safety checking and then deal with this. It's a bit finicky, probably at some point wants a complete rewrite, but in principle, you can do complete static safety checking of code. Now, the other part of correctness is this missing link between a specification that people have audited and read and made sure that this is a correct spec of a standard and the thing that comes from the implementation. And I'm not going to talk about this much because actually the coolest result in this area is something that Miguel Quaresma is going to explain to you on Wednesday. So big advertisement here on formally verifying Kyber episode 4, implementation correctness. But I'm going to say a few things about this project that I think Miguel doesn't have on his slides. In May 2020, I was stupid enough to make the statement that I'm carefully optimistic that we have the full proof and optimized software done by summer. It's 3 years later now, right? And we have the first paper out of this. And that's not even the complete story. I was also stupid enough to put this in writing. So this project started in 2020 in February as a 4-month sabbatical project. So I went to Portugal and visited Manuel Barbosa, and we had an idea to work on this. I was there planned for 4 months. I can tell you that probably every sabbatical in 2020 did not work out quite as planned. So after a month, everything went into lockdown. I took one of the last flights out of Porto Airport back. I also then changed employers. So I had some excuse that this project did take longer, but it also took, in the end, so far, it's a 3-year effort with 12 authors. We had massive improvements to the Jasmine programming language, also to EasyCrypt. And The problem of this is a little bit that this is a per implementation effort. So these security proofs you do once on the specification, and then it's the law, right? Then that's established. But for these functional correctness proofs, every time we're optimizing for a different architecture or a different parameter sets, well, we need to redo the functional correctness proof. Which takes me to ongoing work and challenges. The obvious big challenge is that for this step of the functional correctness proof, we need more proof automation. We're currently working together with Woyin Yang and Mingxian Tsai and Boyao Wang on integrating EasyCrypt and Jasmine with CryptoLine. CryptoLine is a tool, maybe some of you were at CHES last year and remember this formal verification talk of entity implementations. It does automated proofs or semi-automated proofs of branch-free arithmetic circuits or code. And that is exactly what EasyCrypt is not so good at. So if we can say, well, for these blocks of arithmetic, we get automated proofs, and then we can use an EasyCrypt to puzzle them together to the full scheme, that would make life a lot easier. There's also been some discussions to do automated equivalence proving so that when we have two implementations, say a reference implementation, optimized one, we can automatically prove that they're doing the same thing. Then I talked about Spectre v1, and I think it's a very neat result, but Spectre v1 is only part of the Spectre story, and that is only part of the whole microarchitectural attack story. We can protect against some other variants of Spectre actually quite easily. So Spectre v1 is very easy. That would be exploiting indirect branches, and Jasmine does not have indirect branches, so we're good. Spectre v4, there's a hardware countermeasure, or say microcode countermeasure, so we can basically disable that leakage. Which is not very hard to do, and we need to do more benchmarking, but it seems that the impact is not huge. The most important thing, though, is that if we're protecting cryptographic code against Spectre, then in order for this to mean something, we need to isolate that code from the application code. Because Spectre is a global attack. If you have some Spectre gadgets in your web browser code, and your cryptographic keys live in the same address space, then it doesn't help you that the crypto is protected. You'll just use the Spectre gadget in your application code. So we need to really work on getting this cleanly separated into, for example, another process. We need to support more architectures. So everything that I showed you today was targeting 64-bit Intel and AMD CPUs, so x64 architecture. We have now support for 32-bit ARM, specifically the ARM v7-ME, so the Cortex M4. And this works. It will need some more people to use it and play with it and give feedback on it, but that's there. Santiago is currently working on supporting OpenTitan's OTBN, so that's the OpenTitan big number coprocessor, and we want to target that from Jasmine. And then it's very early work in progress, as in we've sat together for 2 hours and discussed it. We're looking into 64-bit ARM CPUs, so ARM v8 and RISC-V. And then one thing that I would find very interesting, so once we have all of this formally proven and we have very strong guarantees and we have really high confidence that the code is good, if you're thinking about what could still go wrong, that's at the interface to the caller. And at the moment, what we have is that the contract to the caller, it's documented for libjade, at least for chems it is, and we will do it for the other things as well. But it would be cool to have this this contract between caller and callee checked or ensured somewhat more formally and not just through documentation. In that context, it would also be interesting to understand if we can enforce stronger safety notions. So, for example, what Rust requires to call unsafe code and actually make that call safe, what exactly we need to do there. However, the really big challenge that we're facing is that I think as a community, we should at some point get to making high assurance tools and this whole idea of how we're building cryptographic software more mainstream and maybe at some point even the default. And I really think that this is the right thing to do. That's the right direction to go into. And I highly encourage you to join that effort. So if you're interested in really joining, go to formosacrypto.org and sign up for the Zulip. There's a link there. See what else we're doing. It will also already be super helpful if you're saying, I would just be happy to use the results. For example, I would be happy to use your formally verified Kyber implementation. You can just go to the libjade. It's one assembly file that you can grab out of there and drop into your code base and start using it. And we'd be super happy to have feedback on this, what works, what doesn't work, what else you would need. And with this, I would like to thank you for your attention.
Peter, or the question talk? I think it's turned off, right? Is it on or off? Yeah, just finish. So are there questions from the audience? I'm sure we have time for a couple of questions.
Yeah. Also, yeah.
You made early on a remark about the risks of function calls and that you try to avoid function calls and prefer inlining. Can you elaborate a bit more? Just
so
performance or other reasons?
So that was not because of a risk. That was simply because Jasmine, the compiler, did not support function calls at the time. So I just implemented everything, and all functions were inlined because this is the only thing that Jasmine could do. And then when I realized that this is not going to work, I told Vincent and Benjamin at the time, look, if we want to do post-quantum crypto with Jasmine, we need function calls. And that's what led to more compiler development and all of this. Yeah.
Yes, Amir? It's a question.
Thank you. I was wondering, do you have any plans on how to deal with when you want to use some part of the hardware to accelerate part of your implementation?
So to some extent, this is already supported. So for example, the AES-NI instructions would be part of a hardware accelerator, and you can just use them through intrinsics. That works. In the OTBN compiler, I mean, I should ask Santiago to answer that one, but they well, they have these big integer registers, 256-bit wide registers, and this is just accessible through the compiler. We actually, I think there's going to be types for this where you can just say, well, we have a 256-bit integer and we're just adding 2 of them, and then that will work. So yes, but if there are features to accelerate, in particular, certain parts of crypto, make them accessible. Yeah.
There's one in the back there.
Thanks. You said that the compiler does not schedule code and spill registers.
Yeah.
And I was wondering, why is that? I mean, I think it would be more efficient or more faster code. Does it make verification faster, or where is the problem to implement this?
This comes a bit from the original spirit of Jasmine. So this is inspired by Chasm, which is basically well, assembly preprocessor / language by Dan Bernstein, where also you basically assume that the programmer wants to do it themselves because existing compilers don't do particularly well. We have had at many occasions discussions about a portable version of Jasmine, which would need to give up on a few things that currently Jasmine does. So first of all, you wouldn't have anymore this feature that one line translates to one line in assembly, because it could be that on some architecture there is just no instruction to do it. You would need to do spilling. You would need to give up on the idea that for every variable you can guarantee that it's in a register. And I think our plan is to have a meeting next year in March to discuss this in some more depth. I think the right thing would be for sort of the higher level connecting code, so not speed critical code, to write this in a language which I think the instruction scheduling there is maybe not even so important because it's not speed critical, but at least to have a possibility to write this portably so we can reuse it for multiple architectures and have spill code generation. And then for the really speed critical parts, do exactly what we're doing now, where as a programmer, I have full control. Another option could be to implement a source-to-source translation so that you're basically trying to restructure Jasmine programs and reschedule them and assist in that way programmers to try out multiple strategies, semi-automated or something. That's also something we've been discussing. Yeah.
We have time for one more. Yes. Boyin.
I mean, not really a question, but more like a comment, which is that the crypto line project actually have logical equivalence checking and working, and I'm sort of wondering, like, would that be useful for what Formosa is doing over here?
Yes, so I think it will be. I wasn't sure if I can mention this because the paper isn't online. But yeah, so this is definitely one of the options to look into for automated equivalence checking of programs to also interface to CryptoLine for that, or use the underlying toolchain. I think you're using ABC for this, right? That could be another option. So yeah, this is something on the longer to-do list. Yeah.
And I think we can do one more. So one question just behind you. Maybe the hand is gone. Okay. Any other questions? Oh, a bunch of questions here. So there was one in the center. Or maybe.
Hi. I feel like sometimes with microarchitectural attacks, we learn that a certain behavior leaks. We try to avoid this behavior, then write software which avoids this behavior. And then another microarchitectural attack comes out and still leaks something.
Yep.
Do you think long-term we will just accept that there is leakage and try to provide security in presence of leakage like we do in our side channel attacks?
That's a very interesting question. So I believe for a few of these side channels, like Spectre v1, I like to be on this formal end where we have a relatively conservative way to model what an attacker can do. So the underlying model is that an attacker can choose at every branch to misspeculate. It's completely given in the attacker's control and misspeculate as far as they want, right? So there's no maximum depth. And if in such a conservative model we can give protections with very, very little overhead, I think it's a nice way to address this. I believe that this may change with Hertz bleed. So Hertz bleed feels like something where we won't get a model where we can no model where we can implement efficient cryptography and still prove that there is no leakage. And I think there we will have to work in that right direction. With regards to that point that there's always a new attack and all of this, I think when you're modeling this and when you're coming up with tools to protect against certain things, you notice that your model is right if several new papers come out and you read the abstract and you're like, oh, okay, but we already protect against that because your model was conservative enough and you're still able to implement very efficiently. And you're just like, yeah, okay, sure, you have a new attack and sure, you have a new logo, but this is actually already what we're taking into account. And then you probably did a good job. Yeah.
Okay, thanks.
And I don't think we have more time for questions, but Peter will be here for the whole week.
I will be around.
Yes, let's thank him again for the talk. And as a small token of appreciation from the conference organizers, you get this. From the size of the envelope is either Bitcoin or a picture of Prague.
Wow. Thank you so much.
Thank you.
Wow.
Now we have a 10-minute break for track switching, right? So make sure you go to the right place. And then the program resumes.
Excuse me, do we have Matthias Kanwischer here, please? Do we have Matthias Kanwischer here? Can you come here? Okay. So sorry for interrupting. I would like to thank Matthias for his yesterday tutorial, and I'm sorry I didn't make it yesterday to thank you. So now we have the gift. We have the gift for you.